Hello and welcome to the Planet Earth podcast. Today we're in London beside a stretch of water that's 215 miles long, beloved by artists and first crossed by a bridge built by the Romans 2,000 years ago. It is, of course, the River Thames, and I'm here because of what can be found in the capital's famous waterway. There's also news from the natural world, which includes a fossil cricket's love song, and I'll also be popping into University College London to learn more about the huge body of fresh water recently discovered in the Arctic.
It's over 1,000 kilometres across, so that's the distance between roughly, say, London to Venice, so it's quite a large area of the Arctic Ocean.
I'm beside a section of the River Thames near Waterloo Bridge, which offers one of the best views of the city. St Paul's Cathedral in the distance, one side, and on the other, Big Ben and the Houses of Parliament. 50 years ago, this river was so polluted it was considered biologically dead. Today, though, it's considered one of the cleanest rivers through a major city. Pollutants, though, such as nitrates, harm newborn babies and trigger the rapid growth of algae in rivers, killing fish and choking plants. As a result, nitrates are removed from water supplies, but even so, the amount of nitrates in the River Thames has trebled since the 1930s. Scientists wanted to know why, and so a team from the universities of Bristol, Durham and Cranfield has been studying how nitrates move through the land to end up in rivers, springs and other sources of water. To do this, they used a paper trail of archives containing records of water quality dating back 140 years, the longest continuous record of its kind anywhere in the world. To discuss what they found, I'm with two of the team members, Dr. Nicholas Howden, a senior lecturer in water at the University of Bristol, and Tim Burt, Professor of Geography and Dean for Environmental Sustainability at Durham University. And I'm going to begin by asking you, Nicholas, where have these nitrates in the Thames come from?
Well, a proportion of the nitrate in the Thames has come from sewage effluent discharges. That's largely been controlled in the last 20-30 years. There have been lots of new treatment processes put in place. A lot of that comes from point source discharges, so we can see them, we know where they are, we know who's discharging them, and they've been largely cleaned up as much as they can be and regulated. The component that we've been mostly interested in is looking at the diffuse sources. So those are the sources that are widely distributed throughout the Thames catchment, and that's one of the largest catchments in the UK, and it's some 10,000 square kilometres. So it's a very big area, and that predominantly is coming from our agricultural activity to grow food. So ploughing, fertilising, use of animals, and the natural processes of biological fixation, and also some atmospheric deposition as well. So it's a combination of factors that have come from our use and our more and more intense use of the river catchment, from which all of this water drains to then end up in the Thames.
How does ploughing release more nitrates into the soil, Tim?
Well, ploughing mineralises organic matter. It basically aerates the soil, and you get organic matter being oxidised, and that works through to, first of all, sort of ammonium salts and then through to nitrate. So it's really, it's the aeration of the soil. It's what, in a sense, ploughing is actually about, turning organic matter into nutrients which can then grow crops.
So does this mean then that during World War II, for example, when everybody was being encouraged to dig for victory, and the records that you've been studying have gone back further back in time than that, did you notice an accompanying sort of spike in a way then of nitrate levels?
Yes, we did. In fact, in the First War as well, but the Second World War in particular, there wasn't much use of fertiliser other than animal manures then, but the mere fact of ploughing and widespread ploughing, a huge increase in the area of land under the plough, and that does show through. It showed through to an extent straight away, but it also showed through in a big delayed response which came several decades after the war. But yes, you can definitely see a link between Food for Victory and all those sorts of campaigns and the water quality in the Thames decades later.
I know that, Nicholas, one of the important things here is about when you saw the link as well. It took time to get those nitrates from the surrounding land into the River Thames.
Yes, that's right. So what we've tried to do is to estimate what the inputs were in any particular year, and then we've used this long record of what was going on in the river to try and match the inputs to the outputs using a series of stores. So in this case, 2 stores, one which is runoff, so that's the water that hits the land and it makes its way to the river in that year. And then there's a second store, which is a groundwater pathway, and so the water that falls in any particular year takes nitrate with it, and then it ends up in the river sometime later. And in producing our model, we allowed that delay time to vary up to a number of decades, from 0 to about 50 years or even more. And what we found was, by using the estimated pattern of inputs that we'd come up with, by considering what fertilisers we used, how much ploughing there was, how many animals there were in any year, we were able to match that input to what we actually observed in the river, and by doing that we can estimate what these different delay times are and how long it takes for something we do in, say, 1940 to reach the river. It turns out the answer is it reaches in about 1970, and the split is roughly 50-50, so 50% of what goes onto the land comes out in that year, and 50% is delayed by approximately 30 years.
That's incredible though, isn't it? 30 years. I mean, that's a real sort of case of thinking about the future, isn't it, in terms of the effect of behaviour will have on the land, how it will affect nature around us.
Yes, it is, and we think this is very important because a lot of what we do, we think that if it doesn't have an effect shortly after we've done it, then it doesn't have an effect at all. Whereas in actual fact, to deal with this problem, we're going to have to think in terms of 50-year cycles. And that's because we're dealing with a natural system that has this natural time constant. And it's very important that we start to understand this when we're setting policy objectives, when we're trying to understand how what we do now will affect the future. For example, a team in New Zealand have started to set travel times on their land around certain freshwater lakes and saying, well, you can only have this much nitrate that you can use in this year, and once you've used it up, you're on the 50-year travel time, it can't happen. You can't do anything else for a number of years. So this sort of management strategy is being piloted, and it's the sort of thing that we're going to have to think about. If we want to reduce the levels to the land at the moment, say we can affect a 50% decrease in the runoff. That's the maximum we could affect if we stopped everything now, because 50% of it is still what's happened the last 3 decades. One of the very important things as well is that we talked about Dig for Victory, and that has an image of me going and digging up my garden. Just to put that into perspective, what we're talking about in the Thames catchment as a whole is a 30% change in the amount of arable land that there was. So we're not just talking about people digging up their gardens, we're talking about wholesale ploughing of every piece of grassland that there was, more or less, available for arable crops to be grown. So we're talking about a lot of land.
Mind you, at the moment, there's the potential of a lot of land also being ploughed up, but for building new houses, particularly around the London area and the Greenbelt area. How do you convince politicians then, Tim, that they have to look beyond the 4 years of their next voting term of getting into Parliament and think 30, 40, 50 years ahead? That's not going to be easy.
It's not, because I think the natural tendency is to look in political cycles and assume that any management policy and strategy will have a payback in time for the next election. And I think it will take some very clear-sighted and selfless politicians to say this is a long-term strategy and these are things we need to do over the long term, and I think the nitrate pollution is just one aspect of that, where we may be looking at long-term groundwater levels or long-term changes in other parts of the system. But it is very difficult to get people to put in place strategies where the payback will be, well after my time probably, and it may be our children or our grandchildren who see the benefit of strategies that are put in place now.
Nicholas Howden from the University of Bristol and the University of Durham's Tim Burt. This is the Planet Earth podcast, and as you can hear, I've left the banks of the River Thames and have travelled just over a mile north to the Centre for Polar Observation and Modelling at University College London. Recently, British scientists discovered a dome of fresh water in the Arctic Ocean using 2 European Space Agency satellites. And the lead author of the study was Dr. Catherine Giles here at University College London. First of all, Catherine, could you describe what this dome of water actually looks like?
Well, if you imagine you're looking down on the Earth over the North Pole and you can see the Arctic Ocean, if you cast your eyes over to Canada, then go north of the Canadian coastline, then you're in the Beaufort Sea. And in the Beaufort Sea, there's a circulation system called the Beaufort Gyre. So that's a rotating dome of water. It rotates in a clockwise direction. And what we've seen from the satellites is that dome increasing in height. The area is it's over 1,000 kilometres across. So that's the distance between roughly, say, London to Venice. So it's quite a large area of the Arctic Ocean.
And when you say a dome, are we talking like a huge Millennium Dome sort of rising of water above the sea surface?
I imagine it more like a contact lens rather than a Millennium Dome, but it's still quite a large amount of water. It's about 8,000 cubic kilometres of fresh water, which is roughly about 10% of all the fresh water that's stored in the Arctic Ocean.
Now, did you have clues that there was this body of fresh water in among a salty ocean?
Well, yes, measurements taken from ships and moorings have shown that there's been an increase in fresh water, say, over the past 15 years or so. But it's really difficult to make measurements in the Arctic because of the cold, dark winters, and the ocean itself is covered by a layer of frozen seawater, so it makes it hard for the ships to break through. So this is why this satellite data is really useful. It helps to tie these snapshots of data taken from the ships and from the moorings to give us an idea of the overall picture of how the Arctic Ocean is changing.
Now, you were using 2 European Space Agency satellites, ERS-2 and ENVISAT, which is sort of the double-decker bus analogy always gets used on this, but it is a huge, huge environmental satellite. Were they both looking at the saltiness of the ocean or sea surface height in order to work out that, hold on, we've got this enormous amount, and it is enormous, amount of fresh water in the Arctic?
What these satellites do, we use an instrument on board them called a radar altimeter. And what that does is measure the elevation or the height of a surface. Now, as I said, the Arctic Ocean is covered by a layer of frozen water known as sea ice. But as the sea ice moves around, it breaks up and it exposes bits of the ocean, and the satellites are sensitive to those bits of the ocean. They can see them from space and we can measure how high they are. So the data that we're using is actually looking at changes in the sea surface height, and from that combining it with data from another satellite called GRACE, which measures changes in mass, we can estimate the change in the fresh water.
Now, do you know how this body of fresh water came to be there in the first place? What caused it?
Well, it's well known that the Arctic Ocean gets fresh water from rivers running off into the ocean itself. So, again, if you imagine looking down on over the top of the Earth, over the North Pole, the Arctic Ocean is surrounded by land. You've got the Russian side, and then Canada and America and Greenland. Now, as we go into the summer, the rivers on that land start to thaw, and as they thaw, that fresh water kind of pours into the Arctic Ocean. So what we're seeing here is kind of either that water being redistributed around the ocean or it being kind of stored in the Arctic Ocean, whereas it might have kind of gone elsewhere, might have actually left. Now, that's not the only source of fresh water. As the sea ice cover melts, that can add fresh water to the Arctic. And also changes in evaporation and precipitation can also change the amount of fresh water that's stored in the Arctic Ocean.
Is there a possibility that this fresh water could flow into other circulatory systems around the Earth?
Well, what we've seen in our data is that the fresh water that has been stored over the past 15 years, that the winds seem to be controlling that storage of fresh water. So it's possible if the winds then change direction, then that fresh water could be released out of the Western Arctic to the rest of the Arctic Ocean or beyond. And we're interested in that because changes in fresh water leaving the Arctic Ocean can influence the deep convection in the North Atlantic. Now, part of the reason that Northern Europe enjoys kind of relatively mild climate in the winter is because of heat transported by currents that are derived from the Gulf Stream. So this circulation system we call the global overturning circulation system, and that's bringing heat from lower latitudes up to the north in the ocean currents, and as that water reaches the north, it cools, it releases its heat to the atmosphere, and the cooler water, it then sinks, and then more water moves up to take its place. Now, this is a density-driven circulation. The water is sinking because it's more dense. So if you then add less dense fresh water from the Arctic, possibly you could affect that circulation system. And in the past, we've seen that an amount of water of a similar size to this 8,000 cubic kilometres may have influenced this convection in the Labrador Sea, which is one of the areas in the North Atlantic where you get this kind of overturning circulation. However, whether that had an effect on our climate is something that we don't know.
Catherine Giles from the Centre for Polar Observation and Modelling at University College London, thank you very much indeed. And now for a roundup of recent news from the natural world with Tamara Jones from Planet Earth Online. And we're going to begin with news of a songbird with quite an impressive range of flight.
It's pretty amazing, this songbird. I mean, it's quite a small bird. It's a northern wheatear, and it's about the size of a robin. And researchers have attached miniature tracking devices to them to find that their epic migrations are around about 30,000 kilometres every year. That's about 18,000 miles. That's a round trip. And they're travelling from the Arctic to Africa, all the way from sometimes Alaska. So you've got a subspecies that live in Alaska, and you've got another subspecies that live in eastern Canada and Greenland and Iceland. And you might expect the Alaskan species to go down to California if they want somewhere warm, but in fact they travel overland, over sort of Russia, over the Arabian Peninsula to get to eastern Africa to find somewhere warm to spend the winter.
So what will the scientists do now?
The thing is, the very fact that they know that they go to Africa and they don't go anywhere else, they don't go to North America, suggests that we need to take that into account when it comes to conservation and making sure that these birds are okay.
Blue tongue virus now. Now, this is a virus that infects animals like cows, sheep and deer. And in fact, there was a sort of an outbreak in Europe in 2006. And there's been some progress, I believe, now in terms of the spread of blue tongue.
Well, that's right. Well, researchers have discovered that midges, tiny little insects, the midges that bite you in Scotland in the summer, that you might expect that they just get blown around by the wind and they're just completely at the mercy of the elements. But in fact, these midges can fly both upwind and downwind. The midges actually carry the disease, so the animals don't get the disease from each other. And so this means that the researchers can find out a little bit more about how some of these outbreaks might spread in the future.
So there's a sort of an unexpected outcome there from such a tiny little insect in terms of the effect it's having on cattle and sheep. And we're going to end with, I think, a quite incredible story about the song of a fossil cricket.
Oh, this is an amazing story. It's gorgeous. These scientists have found that this fossil cricket, it's basically a cricket that lived 165 million years ago, actually made a sound very similar to the crickets that are alive today.
Which makes you immediately want to say, how on earth did they manage to work that out?
The only way they managed to work it out was that the fossil was so well preserved, which meant that its wings were perfectly preserved. So they could figure out the noise that this cricket would have made when it rubbed one wing against the other.
I assume then one of the scientists must have the equivalent of a back catalogue of cricket noises, and knowing how crickets make the noise normally, which, as you say, is rubbing their wings together and ridges of teeth, they can work out then that what the tone would be as well, because not all crickets must make the same noise.
No, exactly. It depends on the number of teeth on one wing and the way it rubs it against the other plectrum on the other wing. So these researchers, they actually compared the shape of the wing and the shape of the teeth with crickets that are alive today to figure out exactly what sound it would make.
Well, I think we ought to have a listen then to what sound they've come up with. That's incredible. So that's a recreated sound of a 160 million year old cricket, sounding incredibly fresh, but it's the tinkling sound that gets me. It's very clear and crisp. So that would have been heard in rainforests, I assume.
That's what they say, that the rainforest might have been quite dense, so a single tone sound would have actually been projected a lot further than a kind of rasping sound that some crickets today use. So it would have been heard by the dinosaurs for sure.
Tamara Jones, thank you very much indeed. And that ends this edition of the Planet Earth podcast from the Natural Environment Research Council. And you can find out more about all of those stories and more on Planet Earth Online. Don't forget to visit us on Facebook and do follow us on Twitter. I'm Sue Nelson. Thanks for listening.